first lecture will be only tomorrow. All right, and of course I haven't presented a new material. So as a result, so quick introduction ahead of a lecture. But today's material in terms of physics is quite simple, right? And most of you are familiar with that, right? So first, fundamental law, which of course we're going to introduce, the Coulomb's law, right? Which describes interactions between two point charges. Keyword point charges. So if you, for example, have these two balls charged, and if you position them like this, you cannot treat them as point charges, right? In this case, you cannot just apply Coulomb's law directly. You have to do some integration. It will be reasonably complicated. But if they are, for example, at a distance like this, right, of course, yeah, with a very good approximation, you can treat them as point charges. Okay, somebody, I see there is some action in the chat. Let me turn on the chat. Okay, so some people complain about the audio. Let me check the settings. There should be no jack, mic, headphones. No, everything right. No, the audio is there. Again, so these can be applied for 2-point charges, right? So yeah, I drew pictures in advance. So if you have Q1 and Q2 at the distance r, then of course this charge is going to exert force on that one. So we can describe it as denoted as F1, 2. And of course at the same time this charge will exert force on that one. So we can denote that as F. That is F21 and this is F12. And of course you know that magnitude of this force and magnitude of that force must be the same. Why? Newton's third law. It still works here, right? And of course Coulomb wrote down this fundamental equation. Fundamental, it means that it cannot be derived. It was written based on observations. Right? Okay, so and again, this is the expression for a magnitude of the force. Right, the absolute value of the force. K, absolute value of Q1, absolute value of Q2, and divided by the square of the distance between them. And new universal constant, K, right? So it's, you see, it's almost 9 times 10 to the power of 9, right? Units of charge, coulombs. Right. Let me check the chat. No, it's still the same. Okay, so then, of course, that can be applied for 2-point charges. But what if you have more than 2-point charges, for example, 3, like in this case, Q1, Q2, and Q3. And of course, they all interact. Then the question is, for example, let's find the net force on the charge Q1, on this blue one. So in this case, we'll have to make 3 steps. First, you apply Coulomb's law for this pair of charges, Q1 and Q2, using this law. All right, so F1, 2, and then for these pair of charges, force F1, 3. And then principle of superposition, very powerful principle. You just add them as vectors. Add, and you will get the net force. So stuff which you know this, right, most likely. So now we just need to look at problems. I prepared 2 problems, and the major idea of the first problem is to refresh vector algebra. Lots of students struggle with, when they work with vectors, finding components, finding magnitude, finding direction. And since we're going to do that the whole semester, pretty much almost every class, so of course it must be fresh in your hands. Of course, sooner or later you will be quite comfortable dealing with vectors, but of course it takes time. Okay, so problem 22.43. So what do we have here? 3 charges, sort of like here, which interact. And we need to find the net force on one of those charges. Right. So let me draw the physical situation. Probably I'll start with this. Okay, coordinate system. All right, so let's assume here I have a positive charge, right? Okay, I label it later in a second. So it's a charge 1. Then there will be a charge over here. All right, so let me position it somewhere. Okay, should be like, okay, another positive charge. Again, I will label it in a second. And here, let's assume that we have a negative charge. Minus. And this positive charge is just above this negative charge. Okay, now let me label them. Q1, so this guy, Q1 is 5 nanocoulombs. That is small n nano. Right. Then this Q, that is Q3. Q3, 10, again, nanocoulombs. And this negative one, let's label it as Q2, and that's, of course, negative 5 nanocoulombs. You know what? I need more space. Q2 minus 5 nanocoulombs. Right? Okay, so that's the electrical part. Now let me draw a few dashed lines like this. Wait, that's the ugly dash line. Right. And some geometry. So an additional line, this one, like this. So what is given in terms of geometry? This distance from the y-axis to this charge Q3, or this distance. Let me label it as B, and B is 3 centimeters. Right. You know what, maybe I will use blue for geometry. So B, 3 centimeters. And this distance is A, okay, I will probably write it like this. A is 4. Okay, that's it. That's what is given and what we need to find. We need to find net force acting on this charge Q1. Of course, the question can be about finding, for example, the net force on this charge or on that charge, but the problem asks for a net force on charge Q1. So let me write down. So we need to find F1. Okay, it's the net force. Net force. Right? Okay.
Yes, anything.
Oh. Somebody's mic is on. Okay, off. Okay, so first of all, I usually prefer to draw a nice diagram because it helps a lot. It helps a lot. So let's also do the same. So we need to draw all forces acting on Q1, right? And of course, there will be only 2 forces because this charge interacts with that one, giving us force F13, and this charge will exert force on this one also, and it will be F12. And of course, all these forces I'm going to draw next to charge Q1 because we want to find the net force acting on this charge. All right, so don't draw those forces somewhere, I don't know, next to those 2 charges. It would be very, very inconvenient. All right, okay, so this, of course, this negative charge is going to attract positive charge. Opposite charges attract, right? Of course, we're going to discuss that tomorrow, but of course you all know that, right? So I don't have to convince you in that. All right, so let me draw it here. So this will be F1, 2. Again, guys, if something not clear, tell me immediately, right? So you have mics, I hope. All right, so then, and of course, yeah, I drew it that way, pointed that way, because it attracts. Right? Then this positive charge and that positive charge. Of course, like charges repel. So this charge will be repelled by that one. And of course, so as a result, the force will be drawn this way. All right, so, okay, so this, I will label it as F13 because it's a force between charges 1 and 3. And then, of course, what's next? Principle of superposition, this. So we just need to add these two vectors as vectors. All right, so I will draw it approximately. And this will be the force which needs to be, wait, it's F1, not F2, which needs to be found. Right. Okay. Diagram in this case helps a lot. In your homework, you're going to see very similar problem. Don't skip on a diagram. Be very careful, right? Because almost every semester, some students send me emails, and then after some time, we realized that mistakes were so silly, so simple, right? So the students kind of, oh, damn it, how come that I didn't notice it? Right. Okay, so now picture is here. Now let's discuss this strategy, general strategy of this problem. How should we address it? Sort of like first decisions are made by general, like in the war. So we're going this way, and then, of course, soldiers will do all gory details, right? All right, so let's do the same here. Let's first describe a general strategy of this solution. Let's start with this force F12. Can we find magnitude of that force? Piece of cake, right? A direct application of Coulomb's law. Charges are given, distance is given, we can find, again, I emphasize, it's a magnitude. It's the absolute value of the vector, right? So that's why I put absolute values of Q1 and Q2, right? So here we can forget about this fact that this charge is negative. Okay, we will see it, right? Because we know the direction of this force. I already drew it. So first we can find the magnitude of this force, and then the next step, can we find components of that vector? It shouldn't be a problem for you because it's purely in the x direction. So we should be able to write components. So first we will find magnitude and components of this vector. Then we will do the same for this vector, F13, for this force. Again, we should be able to find its magnitude. It will be slightly more complicated, but not significantly more. And then the fourth step, we will have to find the components of this vector. Again, if we find one of these angles, we should be able to find components. And then after these 4 steps, we will have 2 vectors written in a component forms. So xy component of first vector, xy component of the second vector, and then finding the net vector, components of the net vector is, again, simple. You just need to add corresponding components. You remember vector algebra from high school and from physics 1. So, and that's how we can find components of the F1, vector F1, force F1. But of course, it's not the whole story. We will have to find the magnitude of that force and direction. Okay? So now after this, let's start doing this. Again, as I said, let's start with F12. All right, and again, I will emphasize magnitude. Magnitude of F12. Okay, so let me write it here. F12, of course, it will be K, absolute value of Q1, absolute value of Q2, and divided by the distance between them. Let me label it as R12 squared. What does it mean, R12? It's just the distance between charge 1 and charge 2. Do we know that? Of course we know. It's B, right? Okay, I will probably write values. I usually skip writing numbers, right? It's just because you can easily do it. But in this case, in order to emphasize, well, first of all, because it's the first time, and emphasize on at one point. Okay, 8.99 times 10 to the power of 9. Then absolute value of Q1. Again, I emphasize on absolute values because now we know the direction of the force. So now we don't need those pluses and minuses. Okay, I see that somebody has fixed the audio problem. Great. I just looked at the chat. Q1, 5 nanocoulombs. Nano, 10 to the power of -9. Right? At some point, you'll get used to this. So this is the first place for silly mistakes. Because you're going to see very similar in your homework. Some students forget to use the fact that it's a nanocoulomb, 10 to the power of -9. They just use 5. And as a result, of course, mastering physics doesn't accept the answer. And of course, students start complaining to me, what's wrong with mastering physics? Right? Careful, right? So 5 times 10 to the power of -9 coulombs. Q1, Q2, again, absolute value, so minus will be dropped. So 5 times 10 to the power of -9 coulombs. Now, second mistake. Don't forget to convert this distance, B, to meters. Again, very common silly mistake, right? So it will be 3 times 10 to the power of -2 meters to the power of 2. Most of the time, again, these two simple mistakes. Students forget about nano and conversion to meters. Okay, so of course I'm not going to calculate it. I will just write the answer. Okay, let me look at my notes. The answer is 2.5 times 10 to the power of -4. Units, it's just a force. Nature, of course, electric force, but it's still the force, so newtons. 10 to the power of -4 newtons. Right. Again, that's the magnitude of the force. Right. So now components, as I said, first magnitudes, then components. Components, you shouldn't have any troubles since it's purely in the x direction, so y component is 0, and the whole thing is in the x direction. So as a result, I can write down immediately. So F1 2x equals to 2.5 times 10 to the power of -4 newtons, and F1 2y equals to 0. Okay, let me frame it, for example, with green, because it's not the final result, but of course we will need it very soon. So first part of the problem, we found components of the first vector. Let's do the same for the second vector, for this one, F1, 3. Again, guys, if you're getting lost somewhere, tell me immediately. All right, okay, so let me put here one bullet, here small second bullet. So again, magnitude of F1, 3. So it will be, of course, K, absolute value of Q1 times absolute value of Q3 divided by R1, 3 squared. Direct application of the Coulomb's law, because those are 2-point charges and we can apply it, right? But now R1, 3 is not, it's still simple, but it's not on the diagram. R1, 3, it's at this distance, right, between these two charges. So let me label it up here. R1, 3, right? So that diagonal, right? And of course, finding this diagonal is very simple. You can look at the right triangle, this point, that point, right? It's a right triangle. This angle is 90 degrees. So of course, R1, 3 will be a squared plus b squared and square root out of that sum, right? Okay, so I usually, since some of you first time in my class, I use this explanation box to explain what I'm going to do to move from this point to the next point. Basically, I'm going to expand how I'm going to find R1, 3, right? My professors used it when I was an undergrad student. I found it very convenient and I use it all the time. Okay, so R1, 3 squared equals to a squared plus b squared. And of course, it will be 5 centimeters, right? Okay, maybe I will write R1, 3. It will be 5 times, but of course I will convert immediately to meters. 5 times 10 to the power of -2 meters, right? Because again, we will need meters, right? So that's I call an explanation box, which allows me to explain what I'm doing to move from this point to that point. All right, of course, now I'm not going to write numbers. You can easily do it. Right. R13 is known. I will just write down the answer. Where is my answer? And the answer is 1.8 times 10 to the power of minus 4. Again, newtons. Right? Yeah, it's F13. Okay, so next step, components. Like here, first here we found magnitude, then components. Now the same, magnitude and components. But of course now it will be more, slightly more difficult to find components, because this vector is not along x or y direction. So in order to find components of this vector F13, because that's the magnitude of this vector, and components, let me use maybe green. So components, of course, will be here, this and that component, right? So in order to find those, we need to know either this angle, right, or this angle. It's up to you. Or both of them are great. But in my notes, I decided to use this angle, theta. It's not given, but we should be able to find. And usually, if we have normal semester when we are at school, right, of course, I usually bug students. Can we find this angle? And first students kind of, oh, no, I don't know. But once I ask the question, what can you say about this angle? Okay, let me show this angle, right? And that angle. They're the same, right? Because they're vertical. This angle and that angle. They're created by intersection of two straight lines. They're vertical, they're equal, so this angle is theta. And once I show that, of course, everyone knows, yeah, of course, we can find that angle theta easily. Right, because, yeah, from this right triangle, this point, that point, it's a right triangle. And you can use any function to find this angle. Sine, cosine, tangent, because we know everything about this triangle. We know this side, we know that side, that side. Right? I usually use tangent, because originally is given, this distance is given, this side is given, and that side is given. So tangent of this angle equals to opposite side versus adjacent. Right? You remember properties. Properties of right triangles must be at the top of your head. You will have to use them almost every semester in every class. So sooner or later, of course, you will remember them. So tangent of theta, it will be, again, as I said, opposite versus adjacent. B versus A. In this case, it doesn't matter if you use centimeters or meters, because you're looking at the ratio. Right. Okay, so I will just write down immediately the answer. Theta is, where am I? Is it my notes? Okay, 36.87 degrees. I use more sig figs because it's not the final answer. It's better to keep more sig figs and then at the end round it off. Okay, so now components. Okay, again, don't be afraid to ask if you are getting lost or something is not clear. So now we should be able to find components again, because now we know this side, we know this angle. So x component, it's this side. Okay, maybe I need to use blue, right? So it's this, right? X component, and of course it will be equal to this side. It's basically this is a rectangle, right? And in order to find this side, which is opposite to the given angle, okay, found angle, opposite to angle theta, so we need to use function sine function, right? So hypotenuse F13 times sine of the angle gives us this opposite side. All right, so let me write that down. So it will be F13 x component, right? So as I just told you, sine function. So it will be F13. It's a hypotenuse. Again, just the properties of a right triangle. In this case, it's this triangle. This point, that point. Times sine of the angle, theta. Sine of angle. Okay, and now I will put my marker down and wait until you tell me something. Are you happy about what I wrote? Maybe somebody is not happy.
Yeah.
Everyone must be happy. Yeah.
I think it makes sense.
Yeah.
For you, it looks like it makes sense, right?
Yes.
Okay, great. It's good that some people are happy about this. Okay, maybe somebody is not happy.
Just wondering about the notation when you do like F13 or F12. I feel like I worry that I might, easily misread that at some point as like F12 or F13.
Okay, no. It's a question of getting used to, right? So you need to get used because these form of notations basically used everywhere, right? Yeah, you can you can pronounce it as F12 or F13, right? Again, everyone will be able to understand you, but it's a very, very common and you need to pass that barrier, right? And get used to this, right? Yeah.
Yeah.
We all, at some point, had to get through this.
Since we're looking at,
it seems to be very, yeah.
sorry, I was just answering your question before. Since we're looking at directions, don't you need a negative sign out front?
Okay, at least there is one person who is not happy. All right? Is she correct? Actually, this is pretty much one of the major points in this problem. Okay, maybe the point where most of the students make mistakes at the very beginning. She's absolutely correct. Usually, again, during the normal semester, I bug almost everyone, right? And usually, sooner or later, one or two students start expressing that they're not happy about what I wrote. She's absolutely correct. Look, when you project this vector on the x-axis, right? So direction will be in the negative x direction. On purpose, I didn't show the direction of that component, right? So, of course, I should have drawn something like this. That component of that x component of that vector is negative. And it's not going to, the minus sign is not going to appear from this sine function because we're not using conventional angle, right? You remember conventional angle in the vector algebra is measured usually from the positive x direction in the counterclockwise direction. If we use this angle for this vector, of course, this minus sign will pop up automatically. But since that angle may be conventional, but not the most convenient in this situation, so we use the most convenient angle, this angle theta. And since we're not using conventional, minus sign is not going to appear here automatically from the sine function. So we have to put that sign manually, minus. Be careful. All right, very similar situation, of course, will be in your homework. Right. So it's a very, very common place for mistake. But usually after I address this problem in the recitation class, usually after that students have no troubles. Okay, I will use red to emphasize. So minus, we have to put that minus manually. Agree? So, yeah. Right, so now, of course, angle is given, a magnitude f(1,3) we found. No, not given, everything is found. So the x component, the value of the x component will be, of course, minus 1.08 times 10 to the power of minus 4 Newton. All right? Okay, so now y component, f(1,3) y equals. Okay, so the y component, of course, it's this side adjacent to a found angle adjacent, right? So, of course, to find adjacent side, we need to use cosine function. Again, make sure that you are comfortable with using sine function and cosine function. Lots of students have trouble on that side. So again, I will do the same. f(1,3) times cosine of angle. And now, at this point, if I start asking students about them being happy, most of the students express their feelings that they're not happy about what I usually write at this point, right? Because again, the same, the y component of this vector points downward in the negative y direction. So it means that we have to put here manually minus, because again, we're not using conventional angle, we're using convenient angle. Right? You see it now? So again, there must be minus here. And let me now show the direction of that component, right? So both components are negative. And so the answer in this case is minus 1.44 times 10 to the power of minus 4 newtons. Okay, so these are our components of the second vector. Okay, I can frame them again with green. Right. So it's this and that. Right? And now the next step, principle of superposition. We just need to add two vectors written in the component form. What can be easier than that? Add corresponding components. Right? So now principle of superposition, I put a new bullet. So first, second, third bullet. So now F1, of course, it will be F12 plus F13. First, I wrote in the vector form. But of course, now we need to add corresponding components in order to find components of this vector, F1. So I will write F1x equals to, of course, F12 x component plus F13 x component. Okay, so this is positive, this is negative. Of course, we will have to subtract them. Okay, I'm not going to write numbers. I will write down the answer immediately, right? I think that you're not going to object, right? So it will be 1.42 times 10 to the power of minus 4 newtons. Y component is easier because this component is 0. This y component is 0, so pretty much the whole thing is over here. All right, so but let me write that down anyway. So it will be F12y plus F13y. All right. Of course, I can emphasize that this is F12y, this is 0, right? All right, so the answer is here, minus 1.44 times 10 to the power of minus 4 newtons. Pretty much at this point, you can say, yeah, the problem is done. We know components of the net force. What else do you want? But mastering physics, and of course, in your homework problem, similar to this, the problem will ask about magnitude of that force F1 and its direction. Right. Okay, so magnitude. You know what? I'll probably move to this side. I will separate this introduction by this long line. And usually, again, during the normal semester, if I ask students about magnitude, and first they're not very comfortable. Some students not very comfortable about answering the question about the magnitude. But once I draw a different picture, because now this picture is too busy, lots of information. Now let me quickly draw a different picture. Maybe here. All right. So what we just found. So this is the y-axis. This is x-axis, right? And we found this component of this force F1. So basically, this is our force F1. Approximately here, F1, right? And what we found components. Basically, we found. So this is F1x, and this is F1y. All right? Basically, the question about finding the magnitude is just dealing with the properties of a right triangle, right? So, of course, magnitude of F1 is just a Pythagorean theorem. F1x squared plus F1y squared. because this is just a rectangle, right? So of course, so magnitude, now again, let me emphasize that. Magnitude, so it will be f1 equals square root of f1 squared, f1x squared, plus f1y squared. Okay, numbers are given. I will just use my notes. All right, so the answer will be approximately 2 times 10 to the power of minus 4 newtons. Okay, so magnitude. And now, next, direction. And direction, read the statement of the problem in mastering physics correctly, right? Properly. Direction measured relative to the positive x direction. So basically, we just need to introduce the angle between this vector and the x-axis, positive x-axis. So let me introduce this angle. It's definitely not that theta. It's a completely different angle phi. It's this angle, right? That angle phi. We need to find that angle phi. Again, without that picture, whenever I start asking students, how can we find that angle, right? Even when I just show it on this diagram, lots of students get confused. But once I draw a separate picture, right, most of students see. All right, so tangent of that angle, it's the opposite side. Again, look at this triangle, right? So this point, and that point. You see those 3 points. Right triangle, properties of a right triangle. Tangent of this angle, it's opposite, which is the y component, versus adjacent, which is the x component. And again, in this case, although the y component is negative, we don't need this minus. We're just looking at this triangle. We just need to look at, need to take a ratio of that distance versus this distance, because the angle is not conventional. We're not measuring angle from the positive x direction in the counterclockwise direction. Right. So I can write tangent of phi equals to absolute value of f1y divided by the absolute value of f1x. So again, you can take arctangent easily, right? So I'm not going to do it. So phi will be equal to, yeah, it's almost 45 degrees because we have 142, 1.44, very, very close to 45 degrees. But what if I leave my answer like this? Will you be completely happy? Or if, let's say, I have to write a report to somebody, right? And in my report, I will write, okay, the angle which defines direction of the vector is 45 degrees.
No.
Exactly. Because if I write it like this, everyone, okay, who knows vector algebra, right? Would think that the vector was in the first quarter. But of course, our vector is in the fourth quarter, not the first one. Right? So we can either write, for example, of course, there are different ways of writing. We can write it below, for example, plus x-axis. Or I think mastering physics wants to write in terms of sort of clockwise or counterclockwise. In this case, clockwise from the plus x direction. CW from plus x. I think mastering physics wants to see these CCW counterclockwise or CW clockwise. Or we can write, for example, or of course, if you write minus 45 degrees, again, that will be clear, right? Everyone will be able to understand that your vector is in the fourth quarter. Or, of course, if you want to use conventional angle, of course, it's that one, right? From plus x-axis in the counterclockwise direction. Of course, that angle, I don't know how to label it, alpha. Or, of course, we can introduce, of course, alpha, and of course, alpha will be equal what? Wait, 315, right? Yeah, 315. In that case, of course, everyone will be able to understand you. 315 degrees, right? But in your homework problem, which is similar to this, of course, you'll have to use CW or CCW relative to plus x-axis. Right. Okay, so that's the first problem, which I wanted to discuss. Again, the major goal is to refresh vector algebra, because we're going to use find components, magnitudes, directions pretty much throughout the whole semester. Right. And of course, Coulomb's law and principle of superposition, but again, most of you are familiar with that from high school. Right. Principle of superposition you used in Physics 1 a lot. Oh, we're running out of time, almost. Okay, all right, so the next one. So if you have questions or clarifications, go ahead. Otherwise, I will start discussing the next problem. We wouldn't be able to finish it. All right. So it's about how can we find, for example, the charge of an object. For example, finding mass is simple, right? You take the scale and you can measure mass. How to find the length of something, again, it's a piece of cake, you can use a ruler. But how can you find the charge of an object? And the problem is about this, right? So for example, let's say you have a charged ball. And let's say you have identical ball, but not charged, for example, right? Of course, if you touch them, charge will be equally distributed, right? Somebody entered as a guest. It means that most likely not the app is used. Right, so, okay, so if you touch it, charge will be distributed equally. So now this is charged with Q and this ball is charged with Q. So how can we find that Q? By setting up a simple experiment. Let's say you attached a cord or string to this ball, cord to this one, again, exactly the same, right? Connected to the ceiling and release them. Of course, now the charges are the same, right? Of course, like charges repel. So of course, they're going to repel and they're going to hang at a certain angle without moving, right? So if you measure angles, if you measure some distances, we should be able to calculate the value of the charge, right? Okay, so let me draw the picture. Yeah, I need to erase this. We will finish this problem on Wednesday. Okay, enough erasing for now. This is problem 73. Very similar will be in your homework. Still, chapter 22, problem 73. Okay, diagram is a must. So let's see. This is ceiling. Then we have two chords, right? So let's say this is the first one. This is the vertical line, and this is symmetrically positioned. Okay, I hope. Okay, more or less symmetrically. Maybe slightly lower. Okay, let me increase the size. Right. So what is given? Mass. M is 3 grams, I think. Let me check. I think 3 grams. Yeah. Then, length of these chords given. L, I think it's 1 meter. Yeah. Then you should be able to measure this angle easily. Let's label it theta, I think. Yeah, theta. And of course, this should be also theta because the situation is symmetrical relative to the vertical line. So theta is 20 degrees. So that's what is given. And then we should be able to find charge. Of course, charges are the same, but they are not given. So what needs to be found? Q. Okay, now I can erase the rest. Okay, so at least today I want to discuss the, again, before we start getting into the gory details, right? Usually I ask students which equation should we use to start solving this problem. Okay, right. And okay, let me just discuss this couple of minutes, right? Usually students first a little bit not very comfortable, right, with how to start, right? And I usually start with this. Which law, fundamental law, can be used to describe motion of any classical system? It doesn't matter if it's a cat running or cars driving, right, or some stars are flying. Which law can be used to describe motions of any objects at any moment of time, at any point of the universe?
Newton's laws.
Of course, Newton's.
First law.
Which one? There are three of them.
Is
I'm
it
gonna
the
guess.
second one?
I'm gonna guess number 2.
Of course, number 2. That's the meaning. It's not just F equals ma. No, it's a universal law which no one can prove, no one can derive. It was just written based on the observations, right? So Newton's second law. And describing any motion. Of course, in our case, we don't have motion. It's a static situation. But what's so special about static situation? No motion, static situation, right? No motion, it's a special case of a motion. All right? So we should be able to use Newton's second law to describe the situation, but acceleration must be put to 0. That's the beginning of this problem, right? Okay, so after discussing this sort of physics, the most important, the rest after that, we just need to sort of reveal what is inside of Newton's second law, draw all the forces, and we will do it on Wednesday.